Okay, so the new material for today, and we are going to talk. It's you know what? Most of anything you'll need to know today, you actually learned in our last lesson. Today, we're just going to apply some of those statistical things that we learned. So, the first thing we're going to talk about is called a box plot, or you may have learned it in school as a box and whisker plot. And this is a good way to present data so that you can get a feel for what that data is like. Like, for instance, just looking at this particular box plot, the box plot is pretty much symmetric, so you can get the idea that data is, pretty much symmetric. Sometimes you get a box plot that looks very different than symmetric. In fact, I think we'll get to one example of them. Oh, excuse me, I still have the hiccups. So, here are team one and team two from our lesson that we did the other day. Here's the five number summary. And remember, the five numbers are always the minimum, the first quartile, the median, also sometimes called the second quartile, the third quartile, and the maximum. So we did this five number summary on team one, and we came out with a minimum of 72, and then 72 and a half was the first quartile, 76 was the median, 77 was the third quartile, and 78 was the max. And if you look at this box and whisker plot, the values are down here for the data. If you look at this plot, it shows you that this data is very condensed and packed. Okay, a little heavier toward the top because you're fitting just as much data. 25% of the data goes from the minimum to the first quartile, 25% from the first quartile to the median, which is the line down the middle, 25% from the median to the third quartile, which is this point here, and then 25% all the way to the maximum here. So there's a lot of scores packed into this area right here. Next, for team two, the five number summary worked out to be a minimum of 67, 69 and a half was the first quartile, 76 was the median, 80, was the third quartile, and 84 was the max. And you can see how much more spread out the data is. And if you recall that list of numbers, they were much more spread out. Notice how everything seems closer to symmetric, not exactly symmetric, but closer to it. Okay, so let's try to make one of these box and whisker plots ourselves. So here's a data set. Number of avalanche deaths in the US during 9 consecutive winters. I gotta tell you, I didn't dream up this data. This was kind of handed to me. It's not the kind of thing I usually do data about. So what I would like you to do is find the five number summary and then try to graph the box plot. If you're not able to graph it, it's not a big deal, but give it a shot, okay? Okay. So, first, to find the five number summary, there's a few different ways to do this. One of which is to realize that, hey, I got the median here in the middle. And by the way, when you have a small set of numbers like this is as simple a way to go as any. The median is 26. The minimum obviously is 8, and the maximum obviously is 32. But I need to find the median of the set on the left over the blue line, and also the set on the right over the blue line. The median of the set on the left is the first quartile. The median of the set on the right is the third quartile. Second quartile is also known as the median. So first I find out what's the middle of 13 and 22. I add them up and I divide by 2. 13 and 22 is 35, divided by 2 is 17 and a half. And over here, well, the middle of 29 and 30 is 29 and a half. So here's my five number summary. Minimum of 8, first quartile 17.5, median of 26, third quartile 29.5, maximum 32. So now I draw my box and whisker plot. Okay, here's my mark for my minimum. Here's my mark for my first quartile. Here's my mark for my median. Here for my third quartile. And here for my maximum. I just draw a line in each of those places. And then the first thing I usually do is draw a box around the center one, just by laying in a bottom line and a top line. That makes my box. And then I draw, remember I said sometimes they call these box and whisker plots. These would be considered the whiskers out to the side. So nowadays, much more common to call it a box plot. But back in the day, when I had hair, they called it a box and whisker plot. Okay? So remember, if you're going to find if you're going to make a box and whisker plot, you find a 5-number summary, minimum, first quartile, median, third quartile, maximum. Plot those numbers, make a box in the middle with the line in the middle of the box, whiskers out to the edges. Okay. Now, why variation matters. Now, if I was just to study the average wait time for each of these banks, they would be identical, okay? But it's decreased in the best bank scenario. Over time, the customer satisfaction will be higher since there are fewer surprises. See, if you look at big bank, boy, oh boy, you could wait as long as like 11 minutes. But if you go to best bank, sometimes at big bank it's shorter, but then in best bank it's, pretty consistent, 7 or 8 minutes. The problem with the big bank is if you go in there and you get like a 3-minute wait or a 4-minute wait, and then the next time you go in and you get yourself a 9 or 11-minute wait, you're like, what the heck? But for the best bank, all the wait times are pretty much the same. So you know what you're getting into when you get there. Now, as far as representing this data in a box and whisker plot, they went and found your the important 5 numbers for you, the minimum, lower quartile, median, upper quartile, which are the first and third quartiles, and then the max, and they plotted them onto the waiting time graph. And you can tell just by looking at them that the best bank has a nice little variation. Everything tends to be really close to the average time. Whereas big bank, it's very spread out and you're not sure what it's going to be at all. Okay? All right. Last thing we got to speak of, standard deviation. My oh my, how times have changed. When I first started teaching years ago, this was standard fare. Haha, get it? Standard deviation. It was standard fare for every 11th grader to be able to plot this by hand. That they would be able to take the data and understand it enough that they could create the standard deviation. Now, I should take a step back and say, well, what the heck is standard deviation? Well, it's an oxymoron is what it is. It's like a jumbo shrimp, okay? Standard deviation is the normal amount that you're different by, all right? The normal amount that you're different by. Standard deviation of a data set is the measure of how far the data values are spread around the normal or the mean of the data set. So if you have a big high standard deviation, they're spread way out. And if you have a very small standard deviation, then they're tightly packed. So in the last example of the top graph where everything was tightly packed, we would say, well, that one has a very small standard deviation. But the bottom one, which was so spread out, we'd say, oh, that has a much larger standard deviation. Now, the formula for standard deviation is this. You got to add up the squares of all the deviations from the mean, divide by the total number of data values minus 1, and then square root it. Now, the reason for the squaring and then square rooting is that just makes it positive. That's all it does. See, the problem is some of the numbers are going to be less than the mean and some are going to be over the mean. And if you just go with those numbers themselves, then what's going to happen, is the negatives will cancel out the positives. So in a formula, if we square it and then square root it, we just make it positive. For example, let's say it was -5. If I square -5, I get 25. And then if I square root it, I get right back to 5 again. So all that does is make everything positive. And for standard deviation, there's one formula that divides by the number of values, another one, number of values minus 1. We're going to use the formula that does the number of values minus 1. So here's how you calculate the standard deviation. The first thing you do is compute the mean of the data set. Go figure it all out, right? Add them up, divide by how many there are. Then you find the deviation from the mean for every single data value. So like if there's, say, 9 data values, you got to add them all up, divide by 9, get the mean. And then you're going to do each data value minus whatever the mean is. Then you're going to square them all. Then you're going to add up all of those squares. We're down to step 3 now. Then we're going to divide that sum by the total number of data values minus 1. And then the standard deviation is the square root of whatever you got in step 4. Sounds like a lot of work, doesn't it? Well, let's go through some of these calculations. What we're going to do here first is this. Here's the data values, just for 5 values, 2, 8, 9, 12, 19. And the mean of this set of data is 10. So in each case, you're going to do what it says at the top of the column, x minus the mean. So 2 minus 10, because the mean is 10, is negative 8. 8 minus 10 is negative 2. 9 minus 10 is negative 1. 12 minus 10 is 2. 19 minus 10 is 9. Then we're going to square each of these solutions. So negative 8 squared is 64, negative 2 squared is 4. Negative 1 squared is 1, 2 squared is 4, and 9 squared is 81. Then we have to add all of those up, which in this case we added up to 154. Then I have to divide that by n minus 1. So I would divide by 4, right? Because there's 5 scores. So do 154 divided by 4, which would be 25 plus 13 is 38.25. And then I would do the square root of 38.25. The square root of 38.25, by the way, is about 6.2. All right, so that's one way to do it. And you can do it that way. There's never a problem doing it that way. But remember I told you back in the beginning, every kid could figure it out? That's what every kid would do back in the beginning. You're looking at it. This is what every single kid in 11th grade math in New York State was trained to do. But then something unbelievable happened called the graphing calculator. And with the graphing calculator, life is much easier. You go to Stat Edit. You put the data into List 1. Then you go to Stat Calc. You choose one variable stat, and the fourth one down is S of X, and that stands for the standard deviation. So, pretty easy to do with the graphing calculator, and honestly, that's how I expect most people would be doing it these days. And I'm not a calculator fan at all in any way, shape, or form in the younger grades. As you get older, I become more of a fan, much more of a fan. When younger, I think it's important to learn your number values because there are relationships contained therein which will make you a much stronger math student and develop the logic and reasoning parts of your brain much better. So let's do some calculations here. They start us off. They tell us the mean is 75. So we're going to fill in the rest of this table. 72 minus 75 is negative 3. Negative 3 squared is 9. 73 minus 75 is negative 2. Negative 2 squared is 4, right? Deviation, x minus the mean, deviation squared. So next up, what's 76 minus 75? Because in each case in this column, we're going to subtract the mean, which is 75. So 76 minus 75 is, you got it, it's 1. And what is 1 squared? Please don't tell me 2. 1 squared means 1 times 1, not 1 times 2. So 1 times 1 is 1. Well, the next number is the same, 76. Whew, I like that. We can just copy it down. And for 78, 78 minus 75 is 3. Why did I write 2? I am the king of the stupid mistake, but I got to tell you something. This really takes the cake. That should be a 3. And then when I square it, I would get a 9. This would be a 4 here. Because it said 2, okay? So I squared the 2 to get 4, but this should be 3 and 9. All right. Fill out the whole table. The mean is 75. So from the beginning to the end, fill it all out. Go ahead. So stop and start time here. Okay. So the deviation here is negative 8 because 67 minus 75 is negative 8. Square it, 64. Next up, 72 minus 75 is negative 3. Square it, 9. Next up, 76 minus 75 is 1. Square it, 1. 76 minus 75 is 1. Square it, 1. 84 minus 75 is 9. Square it, 81. Now, if I was actually computing the standard deviation, I would add up all the deviations, which would be 10, 92, 152, 156. I would do 156 divided by 4, because it's n minus 1. So I do 156 divided by 4, which would be 14 plus that be 39. It would be the square root of 39. And then whatever that worked out to be when you do the calculator. Now, there's a range rule of thumb for standard deviation. The standard deviation tends to work out to be about the range divided by 4. And it's the usual high minus the usual low. All right. So the low value is usually the mean minus 2 times the standard deviation, and the high value is typically the mean plus 2 times the standard deviation. Okay. If you have a mean, let's say we're talking about the number of fish caught, and you want the average number of fish caught, the standard deviation, and the average number of fish caught in a day is 10, and the mean, and you find out that the range is 6. So if I have let me give you better numbers. Let's say the standard deviation is 2, and you normally catch 10 fish. Then the low value is typically 2 times the range is 4. So typically the standard deviation in this case would be, if the range is 4, the standard deviation would be 1, because 4 divided by 4 is 1. And the lowest value would be 10 minus 2 times 1 is 2, so that's 8. And the high value would be the mean plus 2 times 1, which is 12. What I can tell you now is that I'm not really overly concerned about this rule. As far as standard deviation go, I want you to understand that it's a normal amount that you're different by. And if you've got a box plot that's very spread out, you'll have a high standard deviation. If you've got a very condensed, tightly packed box plot, you'll have a low standard deviation. Likewise, and that's if you know your box plot first. If you know your standard deviation first, if you know the standard deviation is high, you're going to have a really spread out box plot. If you know your standard deviation is low, you'll have a very tightly condensed box plot. Okay.